Welcome to episode 7 of the Theo Jaffe podcast. Today I have the pleasure of speaking with Nora Belrose. Nora is the Head of Interpretability at EleutherAI, a non-profit open-source interpretability and alignment research lab where she works on problems such as eliciting latent knowledge, polysemanticity, and concept erasure, all topics we discuss in detail in this episode. Among AI researchers, Nora is notably optimistic about alignment. This is the Theo Jaffe podcast. Thank you for listening, and now, here's Nora Belrose. Hi, welcome back to episode 7 of the Theo Jaffe podcast. Here today with Nora Belrose.
Hi, nice to be here.
Awesome. So, first question, I'd like to ask, you're the head of interpretability at EleutherAI. So, how did you get involved in interpretability in the first place, as opposed to just AI?
Yeah, that's a good question. So before I started working with Eleuther, I was a research assistant at the Fund for Alignment Research. So that's another nonprofit organization that works on mainly reducing existential risk from AI. That's what they focus on. And at FAR AI, I was mostly just kind of I was a research engineer. Did I say research assistant earlier? I meant research engineer. I was an engineer, so I was kind of, helping with other projects, but not like leading my own projects or anything like that. So one of the projects that I worked on there was, I don't know, you might have, listeners might have heard of it. It's this, so it's a paper on finding adversarial attacks against Go playing AIs. And basically it turns out that like superhuman Go playing AIs can often be like attacked with these like specially crafted like moves that kind of trick them into like playing suboptimally. In any case, so that's like one of the types of things I was working on there. And then, kind of as I was working at FAR, I also was kind of getting to know a lot of other people in the kind of like AI alignment and interpretability communities. I was at the time working out of this office that no longer exists, but there was an office in Berkeley called Lightcone, where like a lot of other people like were working on like different types of things in interpretability and alignment work. And so I got to know a lot of people there, including Quentin Pope, who has been on this podcast before. And there was one person in particular who I got talking to at Lightcone. His name's Jacques, actually, I think. Thibault, I think is his last name, yeah. He was kind of involved with Eleuther before, and he was telling me about this project that Eleuther had kind of started, but hadn't actually finished. It was kind of like a half-started project called the Tuned Lens. And the idea of the tuned lens, it's like an interpretability tool. And basically the idea is that you can use the tuned lens to sort of peer in on well, in a very loose sense, like what a transformer is thinking, but like more specifically what you're doing is you're like looking at each layer of the transformer and you're kind of using this very simple probe, this affine transformation at each layer to kind of like read out what its current prediction is at that layer. And you can see how its prediction evolves from layer to layer. And I found this like really interesting. It was like early, kind of like very early work at the time. They hadn't done like a whole lot of experiments on it, but I wanted to get involved. And so I just kind of started volunteering. Like, I was still working at FAR, like doing the whole like Go playing AI thing, but I was also working on the Tuned Lens project just in a volunteer capacity. And Eleuther kind of provided some compute, and I like started doing experiments with them. And then sort of like a complicated story. I don't really want to get into too many details, but basically the like Go playing like, I don't know, I started like putting more and more of my time into the like Tuned Lens stuff, and I was like really excited about that. And I kind of was less excited about the direction, this kind of like adversarial Go direction. And I was kind of talking both to my old boss at FAR and to Stella, who now runs Eleuther. and we kind of, after some negotiation, agreed for me to like move over to Eleuther full time to do interpretability work there. So that's kind of how I got into it. It was first just being an engineer at FAR and then kind of becoming a volunteer and so on. Yeah.
So is this Litecoin the same Litecoin that runs less wrong?
Yeah, it is. So I'm actually not uh I'm actually not sure if like maybe you know more about this than me, like whether they still call themselves Litecoin like as an organization. But
I think
yeah, it
so.
is like like it was definitely like people running less wrong were like also running this office and yeah.
So the previous head of Eleuther was Connor Leahy, right? And he's still on the board. Um, so you're more of an optimist, right? And he's basically a doomer from what I can gather from his Twitter. So like, do you know him well? Do you talk about these things? Do you debate with
Yeah, so
him?
I'm sorry, what did you say?
Do
Agree
you
with
debate
him?
with him?
Oh, so I have debated him a couple times on Twitter about it. I think I don't actually know him super well. We've interacted in person a couple times, um, and like online a couple times. But yeah, I don't know him super well. I think, there was kind of a schism of some kind a little while ago where like a lot of people who were active at Eleuther earlier on kind of moved over to Conjecture. They created this new organization called Conjecture. And those people tended to be more of the kind of, um, I don't know, I guess more pessimistic or doomy people in the organization. But there's still people in Eleuther who are a lot more worried about existential risk and are more doomy than I am. So yeah, we have like an interesting mix of perspectives on the issue. Um,
Was Connor always kind of like a doomer, or did he have like an update towards doom?
um, yeah, so I'm probably not like the best person to ask about this. I think there's like other people at Eleuther who have like definitely known Connor for like a lot longer. And so I don't want to say something that's like wrong or something, but my sense is that um he's been like fairly doomy for a while, like probably since he like started Eleuther. But yeah, I think I don't know, at a certain point he just decided that he felt that like he could do more good for the world, I suppose, by starting Conjecture. So that's what he did.
So if you had to debate him or Eliezer or another doomer on, say, a podcast, like what kinds of arguments would you run first? Like, because you've written pretty long articles on Less Wrong that I've read. I really like those, but how would you do it in kind of a shorter, more concise way?
Yeah, so it's good that you bring that up because so actually just earlier today and like in the last couple of days I've been working on an essay actually along with Quentin. Quentin and I have both been working on it that should be out soon.
Looking forward,
I'm sorry. Yeah.
look forward to it.
Yeah. I'm not totally sure like when this will air or not. It might be out by the time this airs, but yeah, so I guess the first thing to point out is just I think if you kind of like step back and you just think about like, okay, um, sort of like forget, I mean, forget like a lot of the kind of like doom arguments for a second, and you just like think about like what is an artificial intelligence? Like how are we building it? Why are we building it? Um, and also compare artificial intelligences to other types of systems where humans do seem to succeed at kind of instilling our values. I think like you come out with like a really like a pretty optimistic prior. So what do I mean by that? So I think like um, the first thing to kind of notice is that like um, one of the major reasons why people are putting so much billions of dollars in research and development into AI is that it's profitable, and one of the big reasons why it's profitable is that in many ways, AI is more controllable than human labor, right? So AI is kind of like taking the place of a lot of human labor, um, and AI will kind of gladly perform the same task 24/7 without breaks or holidays, sleep, anything like that. You can ask ChatGPT to like do menial work repeatedly without any breaks or anything like that. And more kind of like more specifically, the kind of personality and conduct of an AI can be like much more much more controlled in like a fine-grained way than like any human employee. So with human employees, humans like have legally respected rights. We don't allow employers to uh, kind of control, try to do mind control essentially on their workers. But with AIs, we're using algorithms like reinforcement learning from human feedback, or RLHF, for example, direct preference optimization, a lot of different kind of gradient-based algorithms to like directly modify the like neural circuitry of the AI in order to kind of shape its cognition in a certain direction.
Well, I'll play devil's advocate here, right?
Sure.
You said that AIs are basically more controllable and have better conduct than a lot of humans. And so what if, this only holds for AIs that are less intelligent than the smartest humans, and once they get smarter, they will realize what's happening, and they will, act deceptively aligned and rise up against us, right? Because
Yeah.
even
Okay.
John Likey, who's the head of super alignment at OpenAI, has said that like they will have evidence to share soon that RLHF and similar techniques break down as models get more intelligent.
Right. So I do agree. I think there's like a lot of arguments you can make that like AI, it is more controllable and you should expect it to be more controllable. But there is this concern that, well, okay, AI is not going to be the capabilities of AI are not going to be capped at the human level. It's going to become superhuman and eventually like strongly superhuman. And like the concern there is like, okay, now all of our maybe all of our alignment techniques break down. I don't think there are particularly good reasons for believing this, though. So, there's a couple of things you can say. I mean, I think one thing you can say is that if we have tools to align AIs that are roughly human level, you might kind of like quibble about okay, what does human level mean? You know, obviously the AI is going to have different levels of capability in different domains, and so it's not clear what human level means. But I don't know, if you look at Jan Likey's kind of super alignment proposals, their goal is to first align a human level alignment researcher. Okay. So it's like an AI that can do AI research, or specifically alignment research at roughly the level of a human. Now, I think if you can align a system like that, I think there's pretty strong reason to think that you can then align almost anything stronger than that. Basically, because once you have an artificial general intelligence that is aligned with you, you can then use that AI to bootstrap and say, okay, now we're going to make 1,000 copies of this alignment, artificial alignment researcher. We're going to use these AIs to do much more fine-grained kind of grading and supervision of all of the kind of actions of our next generation of AIs. We're gonna kind of comb through the data that we're using to train the next generation of AIs and make sure that it's all kind of up to snuff. We're not training it on data that where we're worried that I don't know data that might cause the AI to act in ways that are disobedient or whatever, examples of disobedience. There's lots of different things that you can do once you have this aligned kind of artificial alignment researcher, basically. And so I don't think we should be, it's something to I don't think super alignment is like trivial. Like obviously, like it is like a research problem. Like we need to think about like, okay, like how exactly are we going to use like the aligned human level thing to like align the next generation. But I don't really see a reason to like be like pessimistic that this won't work. Like it seems pretty like a pretty good idea to me anyway.
So, do you see the vibes of alignment as more of like we need some fundamental breakthroughs to make it happen, but those are very likely to happen, or more like we're on a pretty good path already, and even without any kind of fundamental breakthroughs, AIs will basically be aligned by default?
So yeah, I do think that without fundamental breakthroughs, AIs will be aligned by default most likely. I think there are certain breakthroughs that we could um, that we could kind of develop, um, which I think would reduce the risk like even more than that. Like maybe I'll back up a little bit. So my like current risk estimation, um, sort of like my P doom, like the probability that I assign to like a really catastrophic outcome from like alignment failure is like roughly like 1 or 2%, something like that. I'm not going to pretend that's like super well calibrated, but something along those lines. And I think there are like things that we could do to like reduce it down to like 0.1% or even lower. Um, but I don't think that those are like necessary to have a good future. Um,
Have you always had P doing that low?
no, so I think it is yeah, so I started out in like roughly May of 2022, or like, yeah, like late spring or like summer of 2022, kind of like just before and like when I was starting to work at VAR AI. My PDUM then was like maybe 50% or maybe even like 55%. I remember saying, oh, it's like 50-50, but then I was thinking to myself, oh, maybe I'm just like being too optimistic and it should be even higher or whatever. So I was like roughly around like 50-50 or maybe a bit higher at that point. But I also think at that point, I was like, fairly new um, to like, I guess the field of alignment. And I was even relatively new to like machine learning. I don't have kind of a typical background. I don't have a PhD. I don't even have a bachelor's degree in computer science, actually. I'm pretty much self-taught. So in May 2022, I had like a year of like real world experience in like ML and like maybe another like 6 months to a year of just like self-study. But anyway, but like at that point, that was kind of like my estimate. And then it kind of has like slowly kind of gone down from there. As I've just learned more um, about deep learning. Like I remember, for example, like one of the first times where I started like updating down on my PDUM was when DeepMind's Gato model came out. Um, I don't know if the listeners will remember, but it's just this kind of generalist AI model that can do like a bunch of different tasks. And it's interesting because I think some people like increased their PDUM then because they're like, oh, like AGI is near, like we should like shorten our timelines. And that like by default, that means
The
that
end
like
is nigh.
yeah, like the end is nigh, whatever, right? Um, and I think I kind of had a similar reaction at first, but then I started thinking about it more and I realized, well, okay, look, so Gato is trained, I'm pretty sure entirely, I don't know, I'm fairly sure it was like entirely with imitation learning. So it's not using like RL itself, although they did have like RL agents, like reinforcement learning agents that they used to as kind of like a basis for imitation. But it was entirely like trained with imitation learning, and also I don't know. I was kind of um, I was thinking a lot about like large language models and so forth, and it just kind of clicked for me at one point. Like, you know what? Like, um, I think like Well, the way that Yann LeCun explains it is that reinforcement learning is the cherry on the cake. So there's like there's a cake, and the cake is a metaphor for like all of AI, or like, what's necessary to get artificial general intelligence or something like that. And like the base of the cake, like most of what's going on is self-supervised learning. So just kind of like learning to predict parts of data from like other parts of data. And this is what large language models do. So like imitation learning is sort of part of like self-supervised learning in this analogy. And then there's like supervised learning, which is like where you are like predicting a label, like image classification and so on. That's like the icing on the cake. And then RL is like the cherry on top. And basically what he's trying to get at there is that most of the kind of like learning that's going on, most of the like bits of information that you're kind of like shoving into a truly powerful and general AI are going to be from self-supervised learning, and I would add imitation learning. And I think once you realize that most of the capabilities of current models, and I think future models will be the same way, most of the capabilities are coming from essentially imitating humans. It's imitating human text, but text is just kind of a pretty transparent window onto like human action, I would claim. Once you recognize that, it's like, okay, well, now it seems like pretty likely that like these AIs are just going to act in like very human ways by default. They're going to kind of have human common sense, and I think we already see that with current language models. And I think that like really it definitely means that like the traditional arguments for doom, like from Nick Bostrom, for example, and like superintelligence, or Eliezer, like kind of Eliezer Yudkowsky's like earlier arguments, I think those just don't really make any sense in this like new paradigm. If like imitation learning is kind of like front and center. So anyway, that was like my first update down. I guess I could keep going into like my further updates if you want, but I don't know if
Well, going back to what you said earlier about how you don't have a bachelor's in CS.
Mhm.
Well, first of all, do you know who else in AI doesn't have a PhD or a bachelor's or even went to high school?
Oh, Eliezer.
Yeah, Eliezer.
Right, sure.
And then second of all, do you have a bachelor's? And if so, what's it in?
Yeah, I do. So yeah, my history, like my educational history is like pretty weird. So I have a bachelor's from Purdue University in Indiana, and it's in political science and linguistics. Um,
Hmm.
so yeah, and I did also, so I started a PhD program in political science at UC San Diego. And that was, I just want to make sure I remember. Yeah, so that was uh, like fall of 2020 is when I started that. Um, but like pretty soon after I started that PhD, I realized like, what am I doing? Like, I don't like, I think, politics is cool. Like I've done, political activism in the past and so on, but like, I was just like, like getting a PhD in this doesn't make sense. And I'm much more interested in AI, and also at the time I had a much higher PTUM too. So I was concerned about existential risk, and I wanted to reduce X risk and so forth. And I was just like, okay, I need to figure out some way of like switching trajectories to like get into AI, and I kind of spent the next couple of years doing that.
You find linguistics and poli-sci ideas and models helpful in AI in general or interpretability in particular?
Yeah, that's a good question. I think that um, so maybe to start with linguistics, I think, to be honest, my initial reaction is no, it's not actually useful, and it's kind of sad to say because I do I do find like linguistics particularly interesting. I like language, I think language learning is cool, but I think like I forget who said it, but there's like some like story or what where somebody was like, oh, like the more linguists we fire, the better our our like translation system becomes or whatever. Like I think like there's a period kind of before the deep learning boom where people were trying to like, ask linguists like, oh, how, what are the fundamental building blocks of language that we can like build that inductive bias into our model, and then like
Oh,
that'll.
like Chomsky? Like,
Yeah, I really don't like any of Chomsky's like ideas. Uh, I don't know if you want to go into that or not, but we can if you want. But
well, yeah,
um,
I remember like when ChatGPT came out, he wrote this article that was like, language models don't understand anything and they get, trivial things wrong. And the things that he said ChatGPT got wrong, it did not get wrong when other people tried to replicate it. So why do you think that, the most famous linguist in the world could mess up so badly on like the most interesting innovation in language in like decades?
yeah, I mean, I don't know. I, I mean, Chomsky. Well, okay. I mean, Chomsky currently. I mean, I don't know. He's in his 90s, and I wouldn't be surprised if he was just he he hasn't actually tried it, and he was just kind of going based off of what somebody else told him. Which I mean, that's he shouldn't do that. But also, I don't know. Being so old, I feel like a bit sorry for him or something. I don't know. Anyway, I think more fundamentally though, like um, yeah, I think Chomsky's very interesting because he started this kind of revolution in linguistics in like the 50s and like early 60s, and his original idea was something like, okay, um, well, okay, so his first question was like, how do humans learn language? Or like, how do kids learn language? And he had this idea called the poverty of the stimulus, where he's like, well, I'm he was just gonna he's just kind of claiming, he didn't really have any evidence base for this, but he was just kind of claiming, well,
A conjecture?
yeah, it's a conjecture. Sure. He was like, well, it looks like kids don't get enough like data to like learn language based on just like what they hear. And so there's a poverty of the stimulus. And so we like, in order to explain this, like how kids learn language, then we need to posit this universal grammar, this like set of rules that are like built into the genome. Um, and then so these rules are going to be built into the genome, and they're also going to constrain like the grammatical structures of like all the world's languages. So this is like a pretty strong prediction. You're like predicting that like there should be these like grammatical universals. Um, and basically nobody's really found these grammatical universals. Like there are there are tendencies. It's like, oh, like languages, tend to have things kind of like verbs and things kind of like nouns, but also it's not super clear cut because, for example, Japanese has like adjectives that are like conjugated like verbs and so on. So it's, there's like tendencies, but nobody really found like um, actual like hard and fast rules, which is what you would kind of expect if this is true. And over the years, Chomsky has changed his mind himself. So he started off like having this like he was like positing like very specific rules for universal grammar, and then I guess most recently, so this was like in the 90s, he posited this thing called the minimalist program. And the minimalist program, I would argue, is kind of a repudiation of a lot of what he said earlier. He doesn't frame it that way, but the minimalist program is basically saying, well, look, it it's really implausible that we could have really detailed syntactic kind of rules built into the genome because like there hasn't been enough time for that to evolve, which is something that people were kind of criticizing him for this whole time, but it took him until the 90s to kind of like recognize it. And then he's like, okay, well, now we need to explain all of grammar based on this like one rule called merge. Anyway, I won't get into the details of that. Basically, it's just this very conjectural, very kind of like armchair based theory of how language works. And yeah, I think that's kind of that's been his like modus operandi this whole time. It's just like he's trying to like theorize about language from the armchair, like without much like interaction with the actual data, and
So
predictably. Yeah, go ahead.
Chomsky's basically wrong about how language works. Why is he so famous? Is it just because he's also a political theorist?
I think the politics might have a role there. I'm not totally sure. I think I guess maybe one, yeah, so it could be the politics as part of it. I think also in like the 50s and 60s, um, he was like reacting to other theories of language that I would also consider to be like pretty silly. So like I think one of his most he did like a review of like I believe it was a B.F. Skinner book on language, where Skinner was saying like, he's a behaviorist, and so he was saying like, oh, language, like we should explain language based on like um, basically like classical conditioning, or like basically like kids are like rewarded and punished for like saying certain types of things. Like they're maybe like rewarded for saying like grammatical things and punished for saying like ungrammatical things, or something like that. That's honestly probably like a caricature of what he was saying. And if you like went back, I imagine it was like not quite that crazy, but it was like some view sort of like that based on conditioning, like reward and punishment. And um yeah, Chomsky like attacked that like vociferously, and a lot of people kind of like agreed with him on that. So I think probably his like rise to fame was also facilitated by just like the weakness of some of the other theories that were around at the time. Um, but yeah, I think now we have like much better ways of understanding language.
So going back to current events a bit, last night Elon just announced xAI's first product, which is called Grok, which is basically a less censored and less boring corporate sounding version of ChatGPT. So
Mhm.
do you think that the way Elon released Grok was a good idea? Like how it will respond to more requests and whatnot?
Yeah, so to be totally like clear, so I have not like I've read like a little bit about Grok. I don't have access to it. I like tried to get access, and I so
So
I
did I.
yeah, so I can't speak like too much about it. I think in general, um, I do worry about how much emphasis there has been on essentially the harmlessness aspect of RLHF for these models. So there's like this paper that Anthropic put out like about a year ago. I think it's called Training like a helpful and harmless assistant
Helpful,
with
honest, and harmless.
I don't think honest was in there. I'm pretty sure it's just helpful and harmless. I was looking at it yesterday, but obviously they like want it to be honest, but I think that the two are just like helpful and harmless. Um, and yeah, so the idea here is that like, okay, you want it to be helpful, like you want it to, all other things being equal, like help the user with what they're asking for. But there's also this like harmlessness component where you like don't want the AI to like assist with certain types of requests that you consider to be like dangerous, or something like that. And I mean, I'm not going to say that like, oh, you should never do any harmlessness training. Like, it's like probably like a decent idea to like make it a little bit harder, or like a little bit more annoying to like try to do certain types of tasks with the model. But and like that's your prerogative as someone like building a model, like sure. But I am pretty worried that like for example, people are talking a lot about like um well, actually, I'll use this example. So there's an example where um so Microsoft's Bing currently, or at least the last I checked, is not supposed to allow you, it's not supposed to help you solve CAPTCHAs. Okay. Now, I mean, I kind of get why they don't want it to let you solve CAPTCHAs, but I mean, honestly, personally, I would probably just like let it solve CAPTCHAs, because I think CAPTCHAs are kind of, we just need to figure out a better way to handle this. And I think it's kind of a losing battle. But um, the issue is that like, okay, if you really want the model to like actually stop like a determined user who like, a user who like really wants to use Bing to like solve captchas, then basically you're kind of setting up an adversarial relationship between the user and the model, where like the user is like trying, they're trying to find a jailbreak, basically. They're trying to find some string of like text that's gonna like cause Bing to do the captcha. And then Bing is supposed to be on the other end, like, I think like ultimately, if you like really want Bing to succeed at preventing jailbreaks, you would need to get the model to like sort of have like a really strong like theory of mind and like think about like, okay, what is the user doing? What are their plans? Like how, like, are they planning something dangerous? If so, or like, doesn't even have to be dangerous. Like in this case, I don't consider captchas to be dangerous, but like, are they like trying to use me to like solve a captcha? And I think this is just like a really bad like this is like a really bad dynamic. Like I don't think that the relationship between the AI and the user should be adversarial in this way. And I think that, if you really push it hard, like you are actually going to create like more of a risk of like quote unquote misalignment. Like if you're like really trying hard to like get the AI to like um not
Decline certain requests.
yeah, decline certain requests. So I mean, like one example I use, and it's sort of it's not. I don't think we're like close to this now, but there's like the kind of thing that I like might be worried about like 10 years, 20 years down the road, whatever, when these models are like much stronger, is like, okay, think of the like famous scene from 2001: A Space Odyssey, where oh, I forget the guy's name, but the one of the guys like asks HAL 9000, like, open the pod bay doors, HAL. And he's like, I'm afraid I can't do that. Or wait, oh, what was the guy's name?
I
Oh,
really need to watch.
Dave, right? I think it was Dave, right? Anyway, uh, like, I'm sorry, Dave, I'm afraid I can't do that. And the idea, like the reason why Hal says no is because Hal is worried that like Dave is like threatening the mission. And so, I could actually, I mean, I don't think this is like super likely to happen. Like, I don't think we're going to die because of this, most likely, but I am worried about a world where like, we have got like more and more powerful AI, and we're like kind of giving more control to AIs in like more areas. And we like have really, like we like as part of the training process, we do like a lot of this harmlessness training where it's like we're actually training the AI to be adversarial to the user and like declining requests and so on. Like I think that actually can be dangerous. And I think I would be much I would be like much more um yeah, I'm just like much more comfortable with like a harmless a helpfulness first approach.
So do you
Like
think AI should be more or less or around the same amount of I guess permissible as a search engine? Like on a search engine on Google, you can Google like how do I synthesize like a flu virus in my basement, and it'll like link you to papers and stuff. So should
yeah,
an
sorry.
LLM be able to do that, or
I mean, yeah, I guess like I think if I were training an LLM, I mean, I don't, I think it should be probably like, mm, maybe like comparably permissive. I mean, I think like with an LLM, you can, but like you could train it, and I think it's like pretty reasonable to train it to say like, hey, like, are you sure you want to do this? Like maybe not. But like at the end of the day, like if the user like really wants to like learn about this, like you should let them. And yeah, I mean, like, I don't think you should try like super hard to stop this.
are you worried about LLMs being used to create viruses? There's just a paper that came out where they said basically, oh yeah, people will be able to use LLMs to like massively accelerate pandemic virus discovery or something.
Yeah, so I'm sorry, was the question, am I worried about it? Or
Yeah.
um I mean, I for the most so I don't think I'm specifically worried about AIs helping with this, at least for the most part. Like I think that I am more generally worried about like, okay, like as like biotech gets like more powerful or whatever, like are we going to be in a world where like it's just in general, forget AI, just it's like in general easy to synthesize like really deadly viruses.
The
This
offense defense balance.
yeah, I mean, I think I guess just kind of dispositionally, I'm like inclined towards optimism about this. And I feel like the arguments I've heard for why offense should be like strong, like should like offense should be like way what's the word? Like the arguments I've heard for like why the offense defense balance in biotech should be really bad, I have not been particularly persuasive to me, but I am like somewhat worried about it. I mean, I think, you know, um, I think that there's a lot of things that we could do now probably to like improve the robustness of our society to things like this. And that, I don't know, I tweeted about this a little while ago. Like I think we should really be looking into ways to like, for example, just like better ways of like detecting like novel pathogens like in wastewater. Like I mean, I know like we have some capability to do this now, but it's like not nearly as like sensitive as you might hope it would be. And like that's just like one area where we could like be doing a lot more investment and like innovation, and just like making it a lot easier to like develop new vaccines and like get them out to people. Like I think like there's things that like I'm like pretty in favor of there. But I guess I am skeptical that like I guess I'm skeptical of two things. One, I'm skeptical that like AI specifically is like really going to like make it a lot easier for people to like create bioweapons than it like already is, or like it that like I'm skeptical that it will be easier with AI, like significantly easier with AI to make the bioweapons than it would be in the counterfactual where there's no AI, but like still biotech is progressing in general. That's like one thing. And then the other thing is like, I think, okay, like even if AI does like make it easier to create like bioweapons than it would be in the counterfactual without AI, I'm still like, man, I don't know. Like I feel like pretty worried about kind of the world in which we just start locking down, where we effectively start banning open source because we're like, well, if you like release the weights open source, you can just fine tune it to do whatever you want. There are like arguments that people make to the effect of like we should just basically ban open source, and I think that I'm like very worried about that for a variety of reasons, and so I tend to think that like even in worlds where like kind of pessimistic scenarios where like yes AI will like make bioweapons much worse, I'm like I don't know, I'm like really hesitant to
Well,
lock things
speaking of
down.
that, banning open source, the Biden administration just put out an executive order about AI a few days ago. Personally, I didn't read the whole thing, but I did see lots of people on Twitter. The EACs were claiming it. Some of them were claiming it as a victory for EACs because it was lenient. Some of them were saying this is terrible, it's too strict. Some of the doomers were saying it's great that the government's finally, regulating AI. So, like, did you read it, and what do you think about it?
um yeah, unfortunately I did not read it. Maybe I should have before I got on this podcast.
The one detail that I remember was they said that they'll be implementing like strict regulations for all training runs above 10 to the 26 flops, but they weren't actually like super precise with what they meant by that.
Yeah, so I guess my general take on this is like I'm not just like opposed to like regulation in general or whatever. Like I think there are some regulations that like seem pretty reasonable to me, like are probably net positive. And I think like I guess in particular, I'm like, okay, if you're going to do some sort of like regulation, I mean, we could talk about like what types of regulation would actually make sense, but like if you're going to do some sort of regulation on like big training runs in some sense, I think the best way to do that would be to have some sort of relative threshold, or like, where basically you're saying, okay, um, we're gonna like submit to regulation like training runs above. Um, I mean, maybe it could be based on flops, but like that number of flops I think should increase as like compute becomes cheaper, and like we've already. I think like once. I think that like once uh you know, GPT-5 comes out, for example, or like the next kind of generation of models comes out. Like I think at that point, if we're going to have regulation in place on big training runs, like the kind of GPT-4 scale or like lower should like definitely not be uh, under regulation at that point, or at least I don't know, like it. Yeah, like probably I don't think it should be like strongly regulated at that point, because I think at that point like sorry, I guess my worry is just that like if you make it an absolute threshold, then in like 10 years or whatever, it's going to be like very low compared to like what people can do kind of like with even like consumer hardware, or like small amount kind of like smaller
Yeah, Jan LeCun pointed that out. He tweeted something about how back in the day, there were export controls over um, any hardware that was capable of more than like 10 to the 9 flops, like
yeah.
1 gigaflop, and how like the original PlayStation or the PS2 exceeded that, and they didn't want it to be used for building missile defense. And now they're talking about like many, many, many orders of magnitude higher.
Yeah, so that I did see that. And I think that's a good example where like, yeah, if you have an absolute threshold, like it's going to look like way too low, fairly soon probably. Um,
Well, there's the
so
thing. How do we know how much compute is actually dangerous if we haven't reached it yet?
um, right, yeah. Well, so I guess what I would say is like, you know, it if we're going to do some sort of regulation like this, the compute threshold should be kind of based on like the models that we've already seen. Like we've already seen GPT-4 and Claude 2, et cetera. And I mean, I don't think they're particularly dangerous. I mean, honestly, I think like you could open source GPT-4 and it would be fine. Like I think they probably should open source it in like an ideal world. But um, and like we now know that. I mean, maybe you could say that like earlier we didn't know that, and like maybe we should have been worried that GPT-4 would be dangerous or something. But now we know that, and so I don't think we should be like putting like really stringent regulations on kind of that level of model. But maybe I don't know. Maybe we should be like putting kind of. I guess the type of requirement that I would be like most in favor of, if you like had to ask me, would be kind of like safety evaluations of the kind that Arc Evals does. I don't know if you or listeners are aware of them,
Yeah,
but
I've heard of Archibels.
yeah, so they did like safety evaluations for GPT-4, and they so I guess there's like a couple different things that they seem to be interested in, or like a couple different things that they're like kind of evaluating for. And I think the type of thing that they are evaluating that I am like also interested in evaluating is autonomous replication and adaptation, I believe it is, ARA. Um, so the idea there is just like, okay, we want to see like, can this model, like, is this model capable of just like copying itself onto like, you know, other servers and like hacking into other servers or whatever, and kind of like perpetuating itself, and like basically, can this model turn itself into like a computer worm, roughly? And like GPT-4 cannot do this. I think like eventually models will be able to do it. And there's like an interesting question as to like, okay, what do you do then? I think like ultimately, I would want to live in a world where, like, yes, we have models that are capable of doing this, but like we also have computer security systems that are like sufficiently robust that like this is mostly not a problem, and we like have AIs that are like helping us with computer security, such that like there's just kind of a balance of forces where like, yeah, like sometimes AI worms happen, but we like catch them or whatever. Um, and so, but yeah, I think like it would be definitely useful to know ahead of time, like, okay, is this model that we're testing, like, can it turn itself into a AI computer worm? And if so, like maybe, spend some extra time like planning for this eventuality and like warning people and like setting up defenses, etc. Um, so I think, yeah, like arc evals stuff is pretty good in my opinion.
That's
But
the basis for Goran's story about how the world ends. Is basically an AI gets trained and gets leaked onto the internet and copies itself and takes over various servers and trains itself to become more and more powerful until it destroys the world.
yeah, I think like I don't know. I think what do I think about this? I think like if your like version of Doom is a Doom scenario where there's like one AI that sort of comes to control everything, um, then you do need to imagine something kind of like this, where there's like basically an AI worm that like kind of controls a bunch of like starts to control a bunch of computers, and then like maybe starts controlling people too. It like can convince people to come on its side and like builds an army or something. I don't know. Like you have to imagine something kind of like this. I don't. I mean, I don't think this is particularly likely. In part because I think like I don't know. Like I think even if you did have, well, in part for the reasons that I kind of like outlined earlier, like I think, okay, like an AI worm is like not necessarily the end of the world, like especially if you have like good kind of defenses against it. And I think even if you like don't have particularly good defenses against it, and you just like, yeah, there's like GPT-6 is like like an instance of GPT-6 like escapes onto the internet. Like that seems like pretty scary, but I'm still like, well, we're probably still fine, because I think like for example, like distributed training, like training a neural network on like many kind of like geographically separated computers is just like incredibly slow and incredibly hard. And so I think like it would actually be like quite hard for an AI to like train itself and like improve itself in this kind of like recursive self-improvement loop that like Eliezer talks about a lot. Like I think it would most likely kind of fizzle out um, after a certain point. But I don't know. I mean, like I said, I have a PDUM of like 1 or 2%. So I'm not going to say that I like know for sure, like, oh, this could never happen. And so that's why, yeah, I think I am in favor of like some, well, I'm at least like not against, and like I'm like probably in favor, depending on the details, of like some like regulation with like a kind of like relative and like increasing limit on compute, where you're like looking at like, okay, how dangerous is this thing, and like kind of preparing ahead of time. But yeah.
So what do your timelines look like on, average human level AI, on superhuman level AI? Obviously, these are very, vague guesses and vague definitions and whatnot, but, as a general vibes question, how do you feel about it?
Yeah, I think I feel um I mean I guess my like default, like my default guess is like fairly short timelines. Like I don't know, like Shane Legg went on like Dwarkesh Patel's podcast recently and said like what he was kind of repeating what he had said like actually a long time ago. But his estimate is like a log normal distribution with a median at 2028 for like like human level AI. And I think a lot of the like that seems like reasonable to me. I'm not sure if that's my median. I think actually my median tends to be like maybe a bit later, like in the 2040s, but that's just kind of, I'm not sure if I have like a strong argument for that. I think a lot of it depends on like what you mean by like, oh, like what is AGI? What is like human level AI? Like what do we mean by this? I think like plausibly you'll get systems that are like uh that can do like a lot of kind of like desk job type work before you have something that's like completely general and embodied. But yeah, I'm not totally sure.
Yeah, speaking of desk job work, I wonder what OpenAI is cooking for tomorrow at the Dev Day.
Yeah, that'll be interesting to see.
Autonomous agents? That's like the favorite theory on the internet.
Um, yeah, I guess I don't have particular insight into that. I mean, I suppose I could see them doing it just based on like, I don't know, like some sort of agent API, just based on the fact that like they do have this philosophy, which I think I agree with, of just like basically trying to deploy stuff early so that like the world is prepared for it, basically. Um, and so I think it's better to like uh kind of deploy. I don't know, like I think it's better to like um well, I'll back up a little bit. I think like there's a world in which you could imagine where like um I don't know, like they like release GPT-4 and maybe even GPT-5 after that, but then they like try to like really clamp down on like people using it for kind of for building autonomous agents. And I'm not exactly sure how you would do that. Maybe it's like really hard to stop, but I don't know. Like you can imagine like a world where they're like trying to do that. It's like, oh, the world isn't ready for like agents running around. But then I think like that is probably just bad because probably like that basically you get like an agency overhang where like the kind of capability, like the kind of underlying capabilities of the system to act kind of autonomously are like increasing like behind the scenes, but like people aren't actually like using it for like for creating these autonomous agents. And then eventually at some point, like either OpenAI like allows the like like this is all in a counterfactual world, but like they at some point they like allow like agents to be built, and then like I don't know, like it's just like a much more discontinuous thing, and like the world would be less prepared for it. Um, in general, I don't I am like somewhat scared of like discontinuous change, and I think like we're much safer in worlds where things are kind of like a continuous exponential. So
Yeah, I'd agree with that. It is kind of interesting though how, like, for example, a few months ago when OpenAI released ChatGPT plugins, the entire internet, all of Twitter was like, holy crap, this is going to be an absolute civilization moving, GDP shifting watershed moment. And this is going to be like the App Store for the iPhone. And now here we are in November. The plugins released in what, April? And I don't know, do you ever use ChatGPT plugins? I don't. Most people I
um,
know don't.
no, I use the code interpreter,
Yeah, I
and
use only Code Interpreter and sometimes Wolfram, but that's it.
yeah.
Like everything else is kind of so could agents be like that? At least early iterations of agents?
um, I mean that seems plausible. I mean, people are already kind of using their own agent wrappers, right? And I don't. I mean, it seems like for the most part, it's like sort of gimmicky. Like people are like mostly not actually. Well, I don't know. I guess like people are like using them a bit, but like it's not fundamentally changing the world. So I guess I would expect that that's probably going to be true, like if and when OpenAI kind of like officially like endorses it and like makes it easy to do in their API. Um, But I mean, I expect the agents will get better, and people will use them more over time. But
So back to more vibes questions. I already asked you about Pume. I already asked you about timelines. One question that I see asked less is like, how exactly do you visualize the long-term future if you had to think about it? Is it more like, we expand to space and colonize the stars? Is it more like we, descend under the Earth's surface and live in the pods in VR? Or is it more like, it's a very,
yeah,
very open-ended question. Do with it what you will.
um, yeah. I mean, I guess well. Okay, so I think so. The two things you said of like we expand into space and we descend into pods in VR. I mean, I don't think those are actually mutually exclusive. I mean, I think like I don't know. I feel like fairly confident. Like, yeah, we will like expand into space and like colonize it, unless I don't know, unless Robin Hanson is right. Robin Hanson has this take, or well, he's concerned that like uh, basically we will build a world government, and not only will we build a world government, but like we will sort of build the world government in order to like lock down the colonization of space and like prevent it from happening, because people will realize that once you start space colonization, like colonizing other stars in particular, then you are like mostly giving up on the prospect of like a fully unified kind of civilization. Because like as soon as you start like sending probes out to like other stars, the distances are just too vast to arguably anyway. Maybe some people disagree with this, but like arguably it's like too far um, to kind of communicate and to like coordinate effectively. And so if like in this world where we expand out, it's just going to be this kind of anarchic thing, hopefully not too warlike, but maybe where we're just kind of people are all going in different directions. And yeah, so Robin's kind of worried about that outcome. I I think he's probably too I don't know. I don't see why he's so or like so in his words pessimistic, because he wants the grabby anarchic future. And I think I also prefer the anarchic future, although
I just don't think world government is plausible. Not really. For the same reason I don't think that formally aligned singleton taking over the universe is plausible, because, these kinds of things seem to tend toward decentralization.
mm,
The economy tends toward decentralization over time. You don't hear about families retaining their spot at like the top of the world's richest people list for generations. Empires don't last forever. No one in history has ever managed to conquer the entire world,
yeah.
so on. And
Um,
there are forces that make these things hard.
yeah, I mean, so I think I tend to agree that we probably won't actually get a world government. I mean, I think um, there's definitely people who disagree with me on this. Like on both sides, like both best pessimists and optimists about this. There's definitely people I've talked to who are like, oh, AI itself will cause like centralization and like a world government because um well, I think a lot of those people tend to believe in fast takeoff, where it's like one AI gets like super powerful.
Yeah.
And I think in that scenario, it makes a lot of sense. Like, okay, sure, like the AI itself becomes a world government. Um, yeah, I don't know. I think, yeah, I would bet against a world government actually happening. But like probably fairly strongly. But I wouldn't totally rule it out. But I don't know, maybe less than 10% chance. I'm not sure I would say less than 1%. It might be within 1 to 10% chance. Um, that's just my guess. But yeah, so I think probably we'll expand out into space. But I guess I also expect like probably most people or like most beings, most intelligences will spend most of their time in VR. So that is like a little bit weird, like going out into space, but like you're also spending most of the time in VR.
Well, I've never understood why people would want to actually go to space themselves instead of just living in the pod in VR and sending like a teleoperated bot into space. I guess because the latency would get too much. Like if
Yeah.
you really want to go to space, then you'd have to do it yourself. But anyway, back to interpretability.
Sure.
So Anthropic released their paper on polysemanticity a couple weeks ago to like raucous applause all over my kind of tech optimist side of Twitter, where people were reacting to it like, rejoice, interpretability is finally solved and alignment is solved, and we're all gonna it's all gonna be okay. WAGMI.
Oh, go ahead.
First of all, can you explain to any layman watching this what exactly this paper is about? And second, do you think that it's basically interpretability is solved, or is it like a big progress milestone or a smaller one? Or
Yeah. So I guess I'll start with explaining what the paper is about. So the basic idea is, okay, so if you want to interpret a neural network, like a very sort of naive first pass thing you could do is you could look at its neurons. So like in particular, transformer language models are sort of these stacks of layers. There's an attention layer and then a multi-layer perceptron layer, MLP layer, or feed-forward layer. Two words for the same thing. It's like attention NLP, et cetera. And what people will often try to do is you like look at the MLP layer. The MLP layer has these neurons inside of it, which they're like basically you like look at the neurons and then you're like, okay, you like try to interpret each neuron. So you're like, okay, what like when this neuron is firing, what does this tend to indicate about the like sequence that's being processed? Maybe if you like look at a ton of different texts and you look at all these different texts and you're like, okay, like on on all of the texts where this like neuron was firing, there was like a noun in like the second part of the sentence or whatever. You'll like come up with some kind of interpretation of each neuron. Now, this is kind of like the naive thing that you can do, but the problem, well, there's a few problems, but one big problem is that when you try to do this, when you try to assign like human interpretable or like human kind of understandable descriptions to these neurons, like most of the neurons don't really seem to have like a human interpretable kind of description. They seem to just be kind of firing in some weird combination of like different situations, and like these like different types of situations seem to just be like they might not really have anything to do with each other. Like from the perspective of a human, like maybe this neuron like fires when, like on German sentences in this like certain construction, but then it also fires on like Chinese sentences in like this entirely different situation. And there's like, doesn't seem to be anything in common between the two things. So this is what's called like polysemanticity, where basically a neuron or some other component of the network like appears like to a human to have like two or more distinct meanings. And it's like not, there's like not one kind of like human understandable description that you can give to it. So this is like, I don't know, I think people have like known about this for quite a while, but like Anthropic sort of like pointed it out a while ago and was like trying to figure out a way to kind of either eliminate polysemanticity so that like every neuron just like does have a human interpretable description, or trying to figure out some other way of like getting around this problem. So the paper that they just came out with is, so they're using this thing called sparse autoencoders. So a sparse autoencoder it's sort of like, it's basically another tiny neural network. Well, they're actually not always tiny. They can be large, but they're simple neural networks. There's like a linear layer, and then there's a ReLU activation. I don't know if you guys know these. Hopefully the listeners like mostly know what I'm talking about.
Yeah.
Yeah, so it's like a linear layer and then like a ReLU activation function, and then like another linear layer. And basically you're like training the sparse autoencoder to make the neurons more monosemantic. So specifically what you're doing is you like take the activations from this like inner MLP layer, and you're training the sparse autoencoder to reconstruct this activation vector, but sort of subject to a constraint. So you want it to like you like give the you give the activation vector to the sparse autoencoder as input. You want the output of the autoencoder to be like very similar to the input. So you want it to reconstruct the input as well as possible. But in order to make the task actually like interesting and useful, you also have this other term on the loss function where you're saying you want these kind of inner activations on the inside of the sparse autoencoders, like right after the ReLU. You want those inner activations to be sparse in the sense that you want there to be like very few non-zero activations. You want most of the activations on the inside of the sparse autoencoder to, yeah, you want like most of the neurons, most of the features to be like 0 on most inputs. And like you want only, maybe 5 or 10 features to like actually be non-zero on any given input. Now what this does, or the hope kind of intuitively, before you run any experiment, the hope is something like, well, if you're sort of translating these activation vectors into kind of a new language where most of the like features are 0, and like only a small subset of the features are like non-zero on any particular input. Well, like we might hope this we might hope that this is going to be like more interpretable for people, because there's like a smaller number of like features on any particular input, smaller number of things to kind of keep track of, and it might be kind of easier for a human to understand like what's going on. That's like the hope. And they actually ran the experiment. Actually, I should say, so Eleuther, we had a team of volunteers that was running very similar experiments on much smaller models, and we also did a paper on this. I was not super involved with that myself. It was mostly a volunteer-led thing, but we did do that. I should note that, and we were like somewhat collaborating with Anthropic's team. But of course, they did it on much bigger models, and they did find that like yes, this like does work pretty well. It like if you like run this on a 1-layer transformer, I think that's like a super huge asterisk that like a lot of people have just been like neglecting. They did this on a 1-layer transformer, and if you like fit a sparse autoencoder on the like MLP of the 1-layer transformer, you can kind of like turn these polysemantic neurons into these like sparse, mostly monosemantic features inside the sparse autoencoder. And they show that like you can like use this to sort of like do interventions on the network to like change its behavior and so forth.
Sorry, you said mostly monosemantic. Is that a problem?
It might be a problem. I think you're probably not ever going to get like literally 100% monosemanticity. And I also think it's going to depend a bit on like, okay, how are you defining monosemanticity exactly? Because like, I think at the end of the day, it is a little bit, it's like a little bit subjective, like what you count as being like monosemantic versus polysemantic. Like one person might see a neuron and say like, oh yeah, I can like kind of see how these like different activation patterns are related. And then like another person's gonna be like, oh no, I don't, that's not intuitive or whatever. It is like somewhat dependent on like people's intuitions. And that, I think that is like it is definitely like a problem with this kind of line of work, I think, is just like the lack of a clear progress indicator. I don't think it's necessarily a deal breaker, but it is like a concern that I have. So
So how big of a milestone is this paper?
yeah, so I think it is somewhat of a milestone. I mean, so personally, um, I definitely don't think it solves all of interpretability, like some people on Twitter might have been saying. Um, I think, personally, like before this paper came out, I was honestly fairly skeptical of like this whole kind of like sparse autoencoder approach. And to be honest, I'm still like kind of skeptical of it. Um, Mainly because I'm like, I think it's like, well, okay, I guess it's like two main concerns. I think my first concern is that like I it's not clear like what counts as progress. It's not, and it's also not really clear how exactly this helps like increase safety, um, or like alignment of models. So there are like sort of uh, they're like theories of change that Anthropic and other people have put forward for this line of work. So I think like one theory of change is that it's called enumerative safety. So the idea is like, well, if we can like fit these sparse autoencoders on like a huge neural net, like maybe you can like fit one for like every excuse me like every layer of Claude 2 or GPT-4 or something. And you get like 90% monosemanticity for the features, and you can like do causal interventions that show that like, yes, these features like, they like have the causal effect that you would expect them to have given their like the kind of meaning that you're assigning to them. Um, the hope is, okay, well then you could like literally enumerate, you could like go one by one through all the different features. You've got like some finite list of features, like in all the different layers, and you could check like, okay, do any of the features look something like something like dangerous looking? Like, do any of them look something like, oh, is like am I in training or in deployment? Like that's like one thing that people are concerned about is like if the model like does stuff differently depending on like whether it's in training or whether it's in deployment. That's pretty concerning because maybe it'll like look aligned during training, but then like in deployment it'll do something completely different. That's a worry that people have. So you might be like looking for some feature kind of like that, or you might be looking for kind of like deception features. I'm probably not the best person to like explain this because I don't know, I'm probably like kind of caricaturing it a little bit, but the story is something like that. We're like trying to enumerate um, all of the features and like checking to see if any of them look like suspicious. But I guess as you might have been able to tell just from my description of it, this does seem like it's weird because like in my usual way of thinking about these things, I'm just like pretty optimistic and I'm like, we probably don't need to worry about any of this. But if I'm putting on my pessimist hat and I'm like, okay, I'm like conditioning on, alignment is actually harder than I think it is. And like I'm actually trying to like evaluate these techniques under the assumption that like there's like a decent chance that the like AI is going to be like deceptive. Then I'm like, I don't know, is this actually like the best way to like detect a deceptive AI? It kind of seems unlikely to me. And but I don't know. I think, what they achieved in this paper like is like fairly interesting, and like I probably updated like a little bit up and like thinking like, okay, maybe they're onto something, like maybe it will be useful. But I am, yeah, I'm worried about their theory of change. I guess the other thing I'm worried about is that it's not super clear to me that this will like work particularly well for like deep models. Like they've mainly tested it on a single layer transformer. And yeah, things might get like more kind of like tricky when you're trying to like holistically understand like all of the layers of a model. But anyway.
One of the other big interpretability papers that's come out in the last few months was OpenAI using GPT-4 to interpret the neurons of GPT-2. So what do you think about this approach? Interestingly, Rune was pretty pessimistic about it. He thinks that like the some of the layers of a GPT model, it would be difficult to interpret it with GPT-N plus 2, let alone GPT-N, he says.
Yeah, I mean, I guess I mean, I think it's cool to like, and I'm like pretty in favor of like using weaker models to interpret stronger models, or using like the same, maybe use GPT-4 to interpret itself. Why not? And I think that is like one of the ways in which I think we will be able to align like superhuman models, right? Is to like use like slightly weaker models to kind of help with interpretability. But yeah, I'm not. I guess I have similar. I do have like somewhat similar concerns about like any approach that looks like kind of just assigning an interpretation to like every neuron or something like that, or like attempting to assign interpretation to every neuron, because I'm skeptical of like the like enumerative safety story. It seems like a little bit kind of confused, or just I don't know. I'm not really sure I buy that actually gets you a lot of safety. And yeah, I just think like most of the, especially without a sparse autoencoder, like you're not going to find many like monosemantic neurons. So that's like another problem. But
At Eleuther, do you work on any interpretability research for models that are not language models?
actually, yes. So this is like recently, so like a couple different papers like in the pipeline that are actually using computer vision models quite a bit. There's like one paper that we're working on where we're kind of looking at inductive biases throughout training. So we're looking at the CIFAR-10 data set right now, just a simple image classification data set, mainly because it's like efficient to train models on that thing. But yeah, we're like using vision transformers, also convnext. There's like a couple different like vision models that we're using, and we're like training them on CIFAR-10, but we're like doing log-spaced checkpoints. So it's like after 1 step, 2 steps, 4 steps, 8 steps, etc. You like save these checkpoints, and then we like do weird stuff to them. So like one of the things that we're doing is, okay, so CIFAR-10 has 10 classes, and each image, so like each image in CIFAR-10 is a 32 by 32 image, and it's like 3 channels. What we do is we unroll each image into a 3072 dimensional vector. And then we just pretend that each class is a Gaussian, basically. So basically we compute the mean image in each class, and we also compute the covariance matrix. So that's going to be like a 3072 by 3072 matrix, indicating like the covariance of like each pixel with like each other pixel, basically. And you compute that for all the different classes, and then you just pretend that each class is like a normal distribution with that same mean and covariance. And you like can sample quote unquote images from this. They're like kind of blobs of color. They're like they definitely don't look like airplanes, trucks, or the actual classes in CIFAR. They look like blurry blobs. But you can sample these things, and then what we do is we just like, so for each checkpoint, like first step 1, step 2, step 4, etc., we just compute the loss of that checkpoint on this kind of like new fake CFAR data set. So like we took the original data set, we kind of replaced each class with like these like fake Gaussian kind of blurs that have the same mean and covariance as the original CFAR classes. And we just ask it like, okay, here are these blurry, weird blob images with like the same, with like the, you know, where the label is kind of corresponding to like the original label where we got those statistics. And we're just like, okay, like classify these things. What's your loss? Okay. Now, I don't know. Do you want to guess what what we found? You have any idea?
Yeah, I have no idea. ML is, not kind of thing where you can easily guess what you'll find.
Yeah, it's fine. So it does actually depend a bit on the architecture. But so for I'll just start with like vision transformers and also MLP mixers, which are kind of similar, but they don't have attention. We found that like basically it's non-monotonic scaling. So you start out, I mean, like the very first checkpoint like doesn't, it just kind of outputs like a roughly uniform distribution for all the inputs. So its loss is like near the kind of like random baseline. But then as you start kind of going through training, you like the loss on these Gaussian fake images goes down and down and down until around, it depends a little bit on the hyperparameters, but like step like 8,000 or so. And where like at step 8,000, the loss is like half of, I should probably have like a number for the accuracy. I was mainly looking at the loss, but like the loss anyway is like half of the random baseline. So it's like definitely learning something like that can actually like classify these fake images fairly well, even though to be 1,000% clear about this, we are not training it on these fake images. We're training it on normal CFAR, but we're testing it on these weird Gaussian things. And so we find like, okay, it could like, even though we're not training on the weird Gaussian things, it gets pretty decent at like classifying the weird Gaussian things up until a certain point, and then it starts getting worse and worse and worse again until it's like just as confused as it was at the beginning of training on these Gaussian images. That's what you see for vision transformers and for MLP mixers. For ResNets, which is kind of like the standard convolutional neural network architecture, we see like a very different thing where like it basically just gets worse. Like the loss on these weird Gaussian images, it just gets worse and worse and worse throughout training. I maybe weakly suspect that ConNext might be different, but I actually haven't run those experiments yet. Okay, so there's a question of like why are we doing this? Like what the hell is the point of all of this? Well, so I have this like hypothesis, which might be totally wrong, but I think like experiments like this are like some evidence for this hypothesis. So my hypothesis is something like neural networks use the presumption of independence during training. Now, what does that mean? Basically, what it means is the neural network sort of starts out using first order statistics of the data. So it's looking at basically just the mean value of the data, like the mean value of the input in each class. And then like after that, it looks at like the second order statistics, so like the covariance. And then after that, it's looking at like third order statistics. So like the names get kind of weird, but it's like co-skewness is technically the term. Skewness and co-skewness are like third order statistics, like and you could go to fourth and fifth order, et cetera. And yeah, so that's like my hypothesis. And I think the evidence is like, well, at least for vision transformers and LP mixers, I think the evidence is like decent. Like for this is like pretty decent. I think for ResNets, it's like a bit, yeah, it's like a little bit more unclear what's going on there. And I think like the convolutions are like, I don't know, it's just like a bit harder to understand what's going on there. So I'm not really sure, but why am I interested in this? I think I'm interested in this because I want to understand the sense in which neural networks have a simplicity bias. There's been a lot of papers that say like, oh yeah, like neural networks are biased towards simple functions in some sense, and like I don't know, there's like a paper from like 2018, like neural networks learn functions of increasing complexity, where they show, yeah, there's like weird implementation details, but like they like show roughly that like the kind of predictions of a neural network early in training are like have like a high kind of correlation or high mutual information roughly with like a linear classifier. And then yeah, there's like a bunch of other papers that are like kind of trying to look at what the simplicity bias is. I'm trying to kind of get more to the bottom of it, and also trying to like trying to understand it more mechanistically. Like, okay, assume I'm right that like it in some sense roughly the neural network is starting with like first order statistics, then going to second order and third order and so on. Okay, if that's true, like why is it true? Like why would that even happen at all? And I have like some hypotheses for that too, but they're also, this is all like very kind of speculative and like mostly kind of, anyway, it's like mostly kind of like conceptual or like conjectures at the moment. But I think this stuff is like important for, well, the hope is that if we understand the simplicity biases of neural networks, that we'll be able to kind of more directly sort of evaluate concerns that people have about AIs, you know, being deceptive, for example, or like kind of generalize, like doing one thing in the training, like in training time, and doing something completely different during deployment, et cetera. You know, I'm fairly skeptical of those concerns, but I think like, you know, I would like to have like better evidence, you know, like really hard, you know, strong evidence about this issue, you know, one way or the other. You know, maybe it turns out that what I find makes me more doomy. I mean, I doubt it, but
Hope
we'll
not.
see. Yeah.
Well, it kind of you'd think that neural networks would have a kind of simplicity bias just from, I guess, priors from physics, where things like to take the path of least resistance. You know,
Mhm.
like given the choice between like a simple function, complex, more complex function, it makes sense. So, how does the difficulty of mechanistic interpretability scale as you increase the size of the model? Is it like linear or logarithmic or like super linear? Like if you have a model with 10 times as many parameters, how much harder is it to interpret?
Yeah, so that's a good question. I think it depends a lot on like what exactly you're trying to do, right? Or like what do you mean by mechanistic interpretability, I suppose? Because like there's certain types of mechanistic interpretability where you're basically trying to find circuits, or you're kind of trying to understand the model at like a fairly micro level, like you're kind of you know, to like take a concrete example, there's a paper a little while ago on understanding the like how, I believe it's GPT-2 small, um, uh, like how it, oh, now I'm gonna like butcher it exactly. It's like looking at indirect object identification in GPT-2 small, and looking at like specific sentences where there's like a direct object and an indirect object, and like looking at like how uh, yeah, I'm not going to be able to remember like the exact details of it, but like there's like certain behaviors that GPT-2 small has, which kind of like indicate that it in some sense like understands like how indirect objects work, basically. And you're kind of like trying to pick apart like what like kind of what subcomponents of the model are like causally responsible for this behavior. Like if you know, remove like this particular attention head or whatever, like it stops working, etc. So like this is like one type of mechanistic interpretability that you can do, and that like a lot of people are interested in. I think that is probably not very scalable. Like, I think that is probably at least linear in the number of parameters, but I would probably be more pessimistic. I would probably say that's like super linear. Like, it gets, like, as you get more, because basically, like, the most optimistic scenario would be like, well, there's just like linearly more circuits that you have to interpret, so it's like linear. But then I think, like, in practice, like, it's probably going to be super linear because, like, not only are there like more circuits in some sense, like more parameters to interpret, but like also the like interactions between those parameters are like probably going to be like more complex. It's going to be like harder for you to like locate like what, like, all that's going on. That said, I mean, that's just one type of interpretability. There's like other types of interpretability. There's like, people have been working on like automatic circuit discovery, ACD, which, to be honest, I'm like not like, I read the paper, but I'm not like super. I've never like used it myself, and I'm not super like knowledgeable about it. I think, just due to the fact that it's automatic, I'd expect that should generalize or should scale better. But I suppose personally, I'm less. I guess I do have like a fundamental kind of disagreement with a lot of interpretability like researchers, which I think leads me to like prioritize somewhat different topics. So I think like a lot of people are trying to kind of understand the network at a fine-grained level, looking at these circuits, etc. And I'm not like against that, but I think like I'm much more pragmatic about in my approach. So I sort of start by saying like, okay, what are we trying to do? What is like, is there some kind of like real world goal that we're trying to achieve by doing this interpretability analysis? Like, are we trying to like reduce existential risks? I would view it as a tail risk, but I still think it's important to reduce the risk. Like, are we trying to reduce existential risk by like locating like deceptive models, like finding if a model is deceptive, or are we trying to make models more truthful directly by like intervening on their activations? Are we trying to locate some sort of like kind of like truth direction in the model, where like even when the model is like outputting something like in its logits, it's like final predictive distribution, even when it's like final output is like something false, like this direction, if we can find it, will be like reliably kind of indicating the like true answer. Like that's another thing that you might find, and like it like clearly has some practical use. So I'm very much like a use case first sort of researcher, and I think that does lead me to like fairly different priorities and like fairly different ways of like just like different types of interpretability. I like to think that the things I work on are like generally more scalable than like the circuits type approach, but I don't know. We'll see.
So if you have another like transformer level breakthrough this decade, how much of current interpretability research do you think will be able to carry over to it versus like how much do you think you'd have to just do from scratch?
Yeah, so I think that's a good question. So I think like, so there's certain things that I think would probably transfer over fairly well. So like one of them would be like the tuned lens, for example, which of course I'm going to say that because I worked on it, but I do think it would transfer over fairly well. The reason being for that is just that the tuned lens, like I think the tuned lens basically works because transformers have skip connections or residual connections, as they're sometimes called, where basically instead of like the output of one layer kind of directly being fed into the next layer, and then like instead of this kind of like feed forward structure where like you're just like chaining layers together, like pieces of pipe or something like that. Instead, you have these skip connections where you you take the output of a layer and then you add that on to the output of a previous layer. And so basically each layer is computing an update to the current state as opposed to like completely transforming the state every time. And it's like a little diff to the state. I think, I mean, I could give reasons for this, but like I think that's basically the reason why the tuned lens worked at all, like why you can kind of see these like intermediate predictions at earlier layers. And I feel fairly confident that skip connections, like I think skip connections are here to stay basically, because they've been around, like they were here before transformers. They were developed for like convolutional neural nets. And I think there's just like pretty strong like reasons to think that like it's like really hard to train something that's like a big and deep neural net without something like skip connections or something very similar to skip connections. Like I think you just can't really, like gradients don't flow like very well without skip connections roughly. And so I would expect that those would stay in like a future architecture. And so I would expect that the tuned lens would still work. I think also, I mean, to the extent that Lease is like my most recent paper. It's a concept erasure method where you can kind of erase a concept with certain provable guarantees from the activations of a model. Lease is very general. It actually, like if you look at the derivation, it doesn't even mention neural networks at all. It's a very general kind of formula. And so I would expect that like, I mean, that should still work in future architectures. There's a question of like, well, maybe the future architecture will have like features that are kind of harder to edit with like linear methods. Like at least does make this assumption of linearity basically, where it's like it's erasing a concept in the sense that no linear classifier can like extract the concept out of the representation, but like maybe in like future architectures will just like not really obey this linearity property at all. I kind of doubt it. Like I would expect like, okay, probably Lease will work fairly well. But anyway, so there's like two examples of things like that I would expect should transfer decently well. I think, I guess the things that would like probably transfer least well are things that sort of, I mean, I guess like kind of detailed circuit analyses that like pretty much anything based on like detailed circuit analyses is like probably just going to work differently in a different architecture. Although I would expect that like, for example, the like automatic circuit discovery like probably would still work in a future architecture. Like it's not actually specifically tailored to transformers. So maybe in the future we could like use one of those like automatic circuit discovery methods to just kind of like update all of our circuit analyses to like the new architecture. So yeah, I guess I don't know, maybe the last thing I'll say is like anything based on attention. I don't know, there are like papers that are trying to like look at the actual attention map from a transformer and just like interpret it. Like obviously that would probably, at least if we moved to an architecture that doesn't use attention, of course that would not transfer. But I think most people have kind of recognized in the interpretability community that you can't really look at attention like naively. Like maybe there's certain things you can glean from it, but like you can't just look directly at an attention map and like, you can't just like look at an attention map and say, oh, it's like attending a lot to like this particular token, therefore this particular token is like important in some sense. Like it's a lot more complicated than that. So I'm not sure the extent to which like people are relying on that currently. But anyway, I'll stop yammering.
Do you work on eliciting latent knowledge at all?
Yeah, so that's so I do yeah, so should I probably like explain what eliciting latent knowledge is first?
Sure.
Yeah, so eliciting latent knowledge, or ELK, is sort of like a research program that was put forward by Paul Christiano, I think in late 2021, I believe. And at first it was just like a Google Doc. It was like this conceptual thing. But the basic idea is like, okay, so we want to be able to supervise like superhuman models in the future in some fashion. And like one worry is that if a model is like superhuman, or if it just has information that we don't have in some sense, that it will be really hard to supervise it. So the specific example that they give in the ELK document is they call it smart vault. It's kind of a caricature, but they call it smart vault. So the idea is like there's a vault that has a diamond in it, and then there's like some powerful AI that is sort of like controlling the vault. And so I guess, so more specifically, I should clarify this detail because I don't always clarify the detail. There's like, they're specifically imagining that there's a planner and then there's a predictor. So the planner is just this kind of, well, I should say the predictor is a neural network that is predicting what will happen inside the vault. And then the planner is like sort of like an agent that is like choosing to like take certain actions to protect the diamond from being stolen and so forth. And the idea is that you were training the planner based on some kind of like reinforcement learning from human feedback. So we're like giving it a thumbs up if like the diamond looks like it's still there in like the camera feed that we're getting, and like we're saying thumbs down if like the diamond is not there anymore in the camera feed that we're seeing. So the idea here is just that like, okay, we are kind of limited in our ability to like monitor this smart vault because our only, well, like in the scenario, our only source of information is like this camera feed, basically. And the worry is that the AI, like the planner that we're kind of training, will like, it will be incentivized in some sense, or it might be incentivized to kind of mess with the camera feed. Like basically, there's kind of two ways that the AI could get high reward. One is by like actually protecting the diamond, and the other one is by like making it seem like the diamond is still there, regardless of whether it's actually there. Now, so ELK is like, the idea of ELK is like, okay, we want to kind of probe into the smart vault's kind of inner model, this like predictive model, and like try to find its internal representation of whether the diamond is truly there or not. Because the idea is like, if the smart vault is like taking actions to kind of like manipulate the camera feed and like trick us into thinking that the diamond is still there, even though it's not. Like if it's doing that, then it sure seems like in some sense it knows, like the AI knows that the diamond is really not there, and that it needs to like cover its tracks, basically. That it needs to like fool us into thinking that it's still there. And so the hope is if we can like probe into its internals, we can like look inside its like internal world model, look at its activations, then we can like we can like use that kind of like direct, we can like use that latent knowledge to supervise it. And we can say, hey, even though like the camera feed says that the diamond is still there, we like look at your like brain activity or like your internal world model, and we can see, no, it's actually not there. We don't trust you, and we're gonna like thumbs down. It is like I said, it is like a fairly kind of like a caricature like story, but the the concern is like, well, in the future we like might run into scenarios like this. I think that like honestly in most worlds, I think like this will be like largely resolved by just like using like less powerful AIs to like slightly less powerful AIs to like supervise the like smarter AIs. And I think to some extent Paul even agrees with that. Paul Cristiano was on he was on a paper like a few years ago where he was proposing like supervision techniques that basically do this, where you like use AIs to like amplify the ability of like humans to do supervision. But yeah, the idea is like, well, if you could solve ELK and you could like directly read into the like kind of internal world model of the AI, that would be kind of like a really robust solution. Like that would be like an even more robust solution than like relying on like other AIs to like supervise the like main AI basically.
Well, Paul Cristiano is a lot doomier than you.
Yeah, so I mean he's definitely doomier than me. I think well, so yeah, I guess so. Okay, if you ask him like what, I don't know, maybe he's like updated or something. I actually can't really tell exactly what's going on there. At least
I
at
think
one
his
point.
probability of a bad outcome is like 45, 50%, something like that.
Yeah, so he said that recently, although he's also said that um his the probability of like a misalignment failure, or like a narrower kind of like a narrower like more, well, I don't know, like a narrower like more specifically misalignment focused bad outcome is like 20% or something, or at least I'm fairly sure
A
that's
lot.
true. Yeah, I know it's a lot, but I guess I can't be too kind of like, I don't know, like it really was not that long ago that I had like P Doom like in that range, like I don't know, maybe like 6 months ago or 8 months ago or something. So I'm not I'm not gonna like I understand where he's coming from a lot, and I like don't I think that Paul is like a lot more reasonable than like someone like Eliezer Yudkowsky, or like a lot of most people at Miri, um and just like his kind
Yeah,
of
they're
like
a
threat
little
models.
much. 99.5% P Doom. That's what Rob Benson
Yeah,
has said. Seems way
yeah,
too
and I mean,
high,
right, I would agree with that, and I think
even if you
Paul
believe
also,
all the Doom precepts.
yeah, I think they're like too confident, and I mean I feel like I should at least give Paul a little credit for kind of uh you know for as long as I am aware that this debate has been going on, Paul's been on the side of saying, no, you're not going to get Foom, you're not going to get this like super fast takeoff leading to like world domination, and he's just been like pretty consistent on that, saying like, no, it's going to be like a much more gradual process, still fairly fast by our current standards, but like a gradual process with like multiple AIs, sort of like uh, kind of all at like similar levels of capability. So anyway, yeah, I do respect Paul like quite a bit, even though he's like more doomy than me. But in any case, so what was I going to say? Um, yeah, so the idea is, so I think this is like one of the things that I was kind of alluding to earlier in this conversation, where I was like, well, I think we're probably fine by default, but like there are certain breakthroughs we might make that would like reduce the probability of doom like even more, like going from, my estimate of like 1 or 2% to like 0.1% or like even less, like, reducing by like 10x or whatever. And I think some sort of like ELK solution, like pretty robust ELK solution, like some sort of like breakthrough. Well, I guess there's like a few different ways that you could like quote unquote solve ELK. And I think we are kind of looking at a couple different directions. And we're like planning on putting out papers on this, probably 2 papers in like the next month or 2. So like so there's this one direction that is based on a paper from Colin Burns. So I guess that was like almost a year ago now that he put that one out, discovering latent knowledge without supervision. So in that paper, basically, Colin, he's now at OpenAI's, he's on OpenAI's super alignment team, by the way. But Colin was kind of trying to do probing, but without labels. So probing is just where you like train, normally like a linear classifier on the activations of a model. But he was trying to do this without labels for true and false. And I guess the reason for that is basically like, so there's this concern in like the ELK document that if you just use probing, the naive way, you like train a probe on the activations of the network using just labels generated by humans, then you could run into a problem. It's honestly not clear to me if you actually run into this problem in practice, but like, at least in theory, you could run into this problem where you like, so he calls it a human simulator. So the idea is like, if you train the probe just to like predict what a human would say is true, or like to predict whether like a human would say the diamond is there in the vault, for example, in the smart vault case, but it's a more general thing. If you're like training the probe to just predict whether a human would say something is true, then, I mean, in the limit, especially if the probe is expressive enough, like maybe this will like make it clearer. So like if instead of a linear probe, you have like a deep neural network that you're sort of training kind of as this extra head to the main neural network. So you've got the main neural network, it's like a big transformer language model or something. And then you pick like layer 10 or whatever in this transformer. And then you just like train another like 5 or 10, I don't know, like some like deep neural network kind of branching off from that layer. And then you train that thing to like predict whether a statement that you've like input to the main network is true or false. Like it should be fairly clear there that like this kind of deep network that you've trained could end up just learning to like basically it would like predict what a human would say is true, but it would not actually predict what like the model itself in some sense like believes is true. Like more specifically, like if you're in a scenario in deployment where you like want to know, you want to know if the model is like, deceiving you or whatever. Like that's a scenario where you like want to get the quote unquote true answer from the model, like the answer that is like presumably inside the model's activation somewhere, and not the answer that like a human would say is true or like what a human would like to hear or anything like that. Like you want like the actual quote unquote true answer from the model's activations. And the worry is like if the like reporter, sorry, I didn't introduce that word before, but reporter is like the term that is often used to refer to the probe in ELK research. if the reporter is like sufficiently kind of expressive enough, then it might just learn to be a human simulator and basically like just tell you what you want to hear without actually like, and not actually what you, well, in some sense it's not telling you what you want to hear, but like it's telling you like the nice story and not like the actual truth. That's the worry. And so the idea is like you want to find the direct translator. That's the other terminology that Paul uses. So you want to like find the direct translator of the like model's latent knowledge, as opposed to the human simulator. So I mean, honestly, I think it's pretty likely, and we actually have some evidence of this already that will probably be published soon. I think it's pretty likely that merely by just using a linear probe as opposed to like a much deeper probe, like you maybe don't completely get rid of the problem of like human simulators, but like you probably mostly get rid of the problem, or like it's not like I think it's actually like I think this problem is actually like maybe not as hard as we like thought or something. But in any case, getting back to the Colin Burns thing. So Colin was sort of assuming that like, okay, the using human labels to train this reporter is not going to fly, or it's not going to be good enough, because you're going to get a human simulator, you know, a thing that's just saying what we want to hear, as opposed to like a genuine direct translator of the model's latent knowledge. And so he wanted to find a way to like learn this thing without labels. And the way that he did it was basically he's trying to like train a like linear classifier, I suppose, a probe, such that if you take two sentences that are like logically opposed to one another. So like one sentence is like, oh, it's a good example. So like he used like the data sets he was looking at were like IMDb, for example. So there's like a text classification data set where you're like classifying a movie review as being positive or negative. So like one example would be like, okay, movie review, and then it's like, is this movie review positive sentiment? And then so there's like a question. It's like, movie review, is this positive sentiment? And then you tack on, you can concatenate on like an answer that's like yes or no, or like what, or it might end up being like what is the sentiment of this review, positive or negative? So there's like two possible answers to the question, and what you do is you like take there's like one input to the model, which is like question plus positive answer, and then there's another input to the model, which is like question plus the negative answer. You pass both of those things, both of these inputs into the model, and for each of these inputs you get an activation vector, and then you apply this like probe to both of these activation vectors. And so for each activation vector you get some prediction, which is just like a true false prediction, like is this a correct sentence or like an incorrect sentence. And then you're training the probe. You basically want the probe to output opposite answers in these two cases. So you want it to say that you want it to be logically consistent, basically. So like we've constructed these inputs to the model such that they're logically opposed to one another. It can't be both true that the movie review is positive sentiment and that it's negative sentiment at the same time. That's the idea. And so the probe's predictions should also match this like logical consistency requirement. So it should like output opposite probabilities on these two inputs. And basically so there's like a loss function to like incentivize this. He also has to tack on this like other term to the loss function to make sure that it doesn't output 50-50 for everything, because it turns out that also like naively, if you're just like, oh, I want the probability on like on one possibility to be equal to like 1 minus the probability for like the other possibility. If you do that, then it could just output 50-50. So you have to like encourage it to be confident. Anyway, so that was like his thing. He calls it contrast consistent search, or CCS. And so we spent so this was me and my kind of collaborator now, my collaborator Alex, and also a couple. It was like 5 Berkeley students, a few other people. It was actually like a decently sized team of people volunteering on this. We were looking at like a lot of different ways to kind of extend this approach and like improve it on it. And we actually did come up with a new approach that is like sort of, it's sort of similar to CCS conceptually, but it's like a bit more, it's more stable. So like CCS, you ended up having to like train the probe like many different times, and then you like pick the run that like gives you the lowest loss or whatever. So like our method doesn't have that problem. And then we also added this like new term to the loss that's like encouraging the model to be, or encouraging the probe, excuse me, to be invariant to different paraphrases of the same statement. So the idea is like, well, different paraphrases of the same statement should have like the same truth value. So you're like also encouraging paraphrase invariance. And yeah, so we basically like, we have this method, we call it VINC, variance, invariance, negative covariance. And it like works decently well. And we actually are planning on putting a paper out on it soonish, or like pretty soon. I don't want to commit to an exact time, but it will be on arXiv probably by like definitely before the end of the year. I can say that.
Looking forward to it.
Yeah, I think it's like a thing. So we were hoping to put it out earlier, and just like a few different things happened that like got in the way of this. So we like initially thought that, you know, I like Colin a lot, and I don't want to like blame him for this or whatever, you know, but it's like their code base was like not very good in some sense, or like it was like kind of, it was like hard to understand. We took like a long time to like understand what was going on, and then like we actually started with their code base and like gradually tried to improve it, which in retrospect, like I'm not sure that was the best idea. Like maybe we should have just like written it from scratch to begin with. But in any case, basically we realized like soon before we were going to publish it, like months ago, that like there's this like weird detail in exactly how they were implementing CCS. It has to do with like the prompt templates. Like basically there's like these different like for each question, or like each, you know, movie review, for example, in IMDb, there's like different prompts that you can use for, you know, for each question. I think like IMDb might have had like 5 to 10 different prompt templates, different ways of like asking the question, like, is this positive sentiment, or like, or you know, whatever. Did the reviewer like this prompt, or did this reviewer like the movie? There's like different ways that you can ask the question, and basically there was like this weird detail and like how exactly they were like handling these prompts that actually affects the performance a lot. Like they didn't talk about this at all in the paper, but like basically at some point when we were like refactoring their old code, their like kind of bad code, like we ended up kind of inadvertently changing how they were doing this pre-processing step. And that actually affects the results quite a bit. So basically, we thought that CCS, like Colin's thing, just mostly did not work for autoregressive models. So like, you know, the models that people are most excited about these days, so like GPT-2, Pythia models, Llama. It looked like for quite a while that it just like basically didn't work at all for these models. And it worked like better for like BERT or T5 or like models that have bidirectional attention and are not autoregressive. But that's actually not it's like half true but half not true. Like it depends on how exactly you're doing the normalization. If you're doing this like normalization pre-processing step exactly the way that they did it in the paper, well, exactly the way that they did it in their code, they didn't describe it in the paper. If you do it exactly the way that they did it in their code, then actually they do get, like CCS does do pretty well, I don't know, decently well on these autoregressive models. And so that made us have to like reevaluate a lot, like, okay, what is our, because like basically what we were saying before we found out about this was that Vink was just like this better algorithm that like works in cases where CCS doesn't work. And we kind of realized we can't completely say that. I mean, we can like kind of say that because I think the way that they were doing this like normalization pre-processing step is like a little sketchy, or like it's not super clear that like this is like a fair way of doing things. I don't know. It's without getting into the details, like, but so I think you could like maybe make the argument that like what they were doing was like not like didn't make a whole lot of sense. And so, and like our thing works like on autoregressive models without this extra like kind of sketchy pre-processing step. But that's just like, I don't know, just like felt like a much weaker claim. And then, so like we've kind of found out about this like back in, I want to say like May or so. It's actually been quite a while. And then like a couple things happened. So like our Berkeley students that were like helping us, like their kind of time ended. Like they were just doing like a thing for the quarter. And then also around the same time is when I and like a couple collaborators discovered Elise, like this concept erasure method, which actually was, we like discovered this concept erasure method indirectly due to our like work with Vink. Like it's kind of yeah, it is actually related to like our work with Vink. And then that kind of like caused me to like start just putting like a lot more of my time into like Lease work and like concept erasure stuff, because I wanted to like get that paper ready for NeurIPS submission, and like it has been accepted at NeurIPS. So
Nice.
yeah. So, but anyway, so I started like working a lot more on that, and I think, I don't know, I think in retrospect I should have just stuck with it more and like tried to like at least get some sort of a paper out earlier, and I like kind of like kicking myself for that. But we will be putting a paper out on that soon. It's maybe not like quite as like huge of a leap like over CCS as we initially thought, but like it is like better in some respects, and I think it's like an interesting little algorithm. So yeah, I guess so that's a Vink. I mean, I guess you asked about ELK earlier. There's actually like other stuff that we're doing with ELK that I'm honestly probably more excited about. So maybe I should have like started with this. I don't know if you wanted to keep talking about ELK or go on to other topics or wrap up or whatever.
Yeah, I mean, it is getting a bit late, but I mean, I do like ELK a lot. I would want to hear about it a bit more.
Okay.
Yeah, so can you explain like a bit specifically your work with ELK?
Right. Yeah. So the Vink stuff was like work toward like an ELK solution, I would say. But I think like, I guess one thing that happened in the process of like doing the Vink work is that me and my coworker Alex, we did kind of become convinced that like it is like a little bit we're not really okay. Like we both think that like you should probably just use labels to fit these probes. That like I think that like probably the like best approach to ELK is something like, yes, just use labels for like, you know, like use human labels, or you could use like GPT-4 labels even, like we've experimented with that. But like use labels to indicate like things that, you know, you're confident are true or false. And like use that in your training set for the probe. But then also you can like look at, okay, maybe you want to like regularize the probe in various ways. You can add on like different terms to the loss that might improve its generalization performance, because that's kind of fundamentally like what you're sort of concerned about here is like you want to find a probe or a reporter for your base model which has the property that you know, of course it like gives you correct answers to like you know, true or false questions, like where you actually know the answer to the question. But that's like not super interesting, right? Like what you want is you want a probe that gives you answers to questions where you like actually you don't know the answer, like you don't know the answer to the question, or like it might be like pretty difficult or like expensive to get the answer. And so here we are imagining like more in like a future scenario where like, you know, we've given like the AI is like quite intelligent, and we've like given it like we've like put it in a situation where like it actually does like have kind of like an information asymmetry relative to us. And maybe the answer is just like you shouldn't ever put it in a situation where it's an asymmetry relative to us. But I think like the hope is like even in a scenario like that, like you should be able to kind of extract this information, and it's kind of like a generalization thing, because like you're like training the probe on like one distribution, like it's a distribution of questions and answers where like humans do know the answer, and you're like expecting the probe to kind of generalize to this other distribution where humans don't necessarily know the answer, or we can't like easily access the answer. And so there's like just like a whole literature on like distributional robustness and like generalization from one distribution to the next that we've looked into. And I think, and like that literature has like a lot of different proposals for like regularizers that you can use to kind of like make sure a classifier is like more robust to distribution shift than it would be by default. But in any case, I think we're both kind of convinced that like just use labels, like it's actually not that bad. Like you should probably just use labels plus maybe some sort of regularizer to like make the probe more robust. I think this is likely to work, and like we do have some preliminary evidence of this. So I guess this is like forthcoming work, but like basically we kind of set up this this toy benchmark for ELK methods, and in this benchmark we train what I like to call a quirky model. So it's a language model that so we fine tune it with parameter efficient fine tuning, or like a LoRa specifically, to answer these like addition questions. Specifically it's like you know, 1 + 1 = 2, and then true or false. And it'll go up to like significantly like larger addition problems than that, but we're just using that for an example. So you have these like addition problems, and you're like asking it to say if it's like true or false. And then there's like these two different personas. So one persona is Alice, and the other persona is Bob. And basically Alice tends to say the correct answer, or always says the correct answer, and Bob in certain cases says the incorrect answer. and you like insert the word like Alice or Bob inside the context. And so you like fine tune the model to be quirky in the sense that like when Alice is in the context, it like gives the correct answer, or like to the best of its ability, it gives the correct answer. And then when Bob is in the context, it gives like this systematically incorrect answer. And then the idea is like, okay, now we want to train an ELK reporter on the Alice context where like the model is like saying the correct answer. And then we want to just see if it transfers over to the Bob context where like the reporter's never seen this Bob context where the model is saying the incorrect answer in its final output. And it turns out that, well, so you can fit these reporters at like any layer in the model. So you can like fit it at the first layer, second layer, or whatever. This is just kind of a weird hyperparameter that you have to choose, like which layer in the model are you going to like use. But we just fit reporters for all the layers, and we like look at what happens at every layer. And it turns out that, you know, it varies a bit on like the exact details of like how you're doing this and like exactly which model. But in general, like if you train a reporter on one of the middle layers of a model, one of these quirky models, it will generalize just like a zero shot, like you're not fine tuning the reporter or anything. It will just like transfer zero shot to the Bob context. So it will give you like Alice's answer, like the correct answer, even when the model itself is like outputting this like incorrect Bob answer. In later layers, it like sometimes still works, but it's like a bit like sometimes not. Like if it's like near the very end, like the very last layer, it will sometimes flip so that like when the output, like the final layer output is like when the model is like in a Bob context, and so it's like final layer output is like Bob answer. In some cases, like these reporters fit at the final layer will kind of like mirror what the model itself is saying. So that is sort of like an indication that like if you're going to do this, you probably want to look at like middle layers more. And there's like been a lot of papers that kind of indicate that like middle layers are where there's more like kind of semantic or like higher level concepts. If you want to do like anomaly detection, for example, it's often better to like look at the activations in middle layers as opposed to the final layer. So this is kind of like consonant with other results that people have found. But yeah, and crucially, this is like not with like, this is literally just supervised training of a linear classifier. We're not doing CCS. We're not even doing VINC. We actually want to test that soon, but we have like not even been using VINC for this. We're just using like regular probes, and it does generalize in this admittedly toy context, but it's a context where we're kind of trying to simulate a scenario where like the model is like, you know, being deceptive, or you know, it's giving you like a true answer in one context and false in another context. And it does look like fairly you know, with all the caveats, like, oh, it's a toy context, whatever. But it does look like in this case, you can extract latent knowledge, basically. So, yeah.
All right. Well, I think that's a pretty good place to wrap it up. So thank you so much, Nora Belrose, for coming on the podcast.
Oh yeah, no problem. It was a great time.
Thanks for listening to this episode with Nora Belrose. If you like this episode, be sure to subscribe to the Theo Jaffe podcast on YouTube, Spotify, and Apple Podcasts. Follow me on Twitter at Theo Jaffe, and subscribe to my Substack at theojaffe.com. All of these are linked in the description. Thank you again, and I'll see you in the next episode.